Good afternoon, everyone. Welcome back. So the first session for the afternoon will be the thin film technology. My name is Kai Liu from ANFF-Q. I'm a professional officer of Queenstown Node. So this is the outline for today's talk. So first I will introduce the thin film. Then the next I will talk about the deposition technique, the PVD, CVD, and followed by the oxidation process. At the end of the talk, I will compare different deposition technique. So first, I will introduce to the thin film. So what is the thin film? So thin film usually is the layer of material with the thickness from nanometer to a few micrometers. If your thickness is greater than 10 micron, usually we don't consider it as a thin film. So why we use thin film? Because thin film has special and distinctive property different from bulk material, like silicon. We can deposit amorphous silicon, polysilicon, single crystalline silicon film, which the property is significantly different from the bulk material. So another great feature for the thin film is the microstructure achievable, which allows us to build the block one by one, which make your device visible. So let's talk about the thin film applications. So thin film, we are using thin film every day in our daily life. So in summary, we classify into 4 different areas for application. The first one will be the microelectronics, which including ICs, LED, solar cell, batteries, those things. And another one is optical coating. So this is for lens, mirrors, coating, and goggles, the sunglasses we're using. And the third one is protective coating, which is to improve the hardness and wear resistance and oxidation resistance. The last one will be decoration. So like you have a coating on your jewelers and the watches to become beautiful. So when we deposit thin film, so we need to know some, like the property of a thin film. So in summary, there are some basic properties for thin film. First one will be physical properties. So including texture, green size wall, this is a physical structure property. So the next one will be the chemical property, which including the composition, stoichiometry, all this is chemical property. And also mechanical property, which include the adhesion, stress, how good is your film, what's the density of the film, whether you have the pinhole defect on the film. Another property is optical. So when you, especially you're doing some anti-reflective coating, you need to know about the transparency or reflective index you need to look at. The last one, especially, is very important for when you make this for devices. If you're coating some insulating material, so it's very important that you have very high breakdown voltage. If you are depositing the metal film, so you want the conductivity as small as possible. So when we do the deposition process, how do we characterize the process? So there's a few properties we need to look at. The first will be the deposition rate, then the uniformity. Uniformity, usually we look at 2 types of uniformity. One is the point to point in the wafer. Another one is wafer to wafer. Because if we are running 100 wafer, we need to look at the uniformity cross wafer to wafer. This will call run-to-run uniformity. Another one is the deposition directionality. So you need to look at what's the application for your deposition. So do you need a directional deposition, like Andy just mentioned in the morning? So if you need a leaf-off process, you need a trench filling process. You need to have a directional deposition. Go to your trench or holes. And another one is non-directional deposition. This is also called conformal deposition, which is give you a very good step coverage. And the film quantity, which I just mentioned, and the cost of the process. So there are few deposition techniques right now. Generally, we can split to PVD, physical vapor deposition, and chemical vapor deposition, and oxidation. This I will cover today. And there's another like electrochemical deposition, like electroplating and electronless plating. I'm not going to cover today. And for physical vapor deposition, I will talk about the evaporation and sputtering. And MB I'm not going to cover today. And MOCVD I'm not going to cover today because those technology is for the 3,5 group material like indium gas 9, indium nitride, 3,5 materials. So for chemical vapor deposition, I will cover LPCVD, PECVD, and ALD. So first, we'll talk about the PVD process. So in PVD process, we have evaporation process and a sputtering process. So PVD, physical vapor deposition, that means so the vapor is physically released from the source and directly transported to your substrate in the gases phases. There's no chemical reaction involved. So typically there are two types of PVD process. One is the evaporation process, usually also called vacuum evaporation, because evaporation is carried out in the high vacuum environment. Another one is the sputtering. Sputtering, there's lots of technique for sputtering process, like DC sputtering, RF sputtering, magnetron sputtering, reactive sputtering, and cold sputtering. So what is the thermal evaporation? So the first one will be, so we use the resistive heating to heat the source and until it vaporizes or sublimates. Then after that, the evaporant will deposit onto your substrate because of the condensation. So in this thermal evaporation process, the mean free path is very important. So the mean free path is the average distance which the molecule travel before collision with another one. So if you have a high vacuum, then the mean free path is much longer. So this mean free path must greater than the distance from your source to your substrate. So this is usually the filament. That's the boat we use for thermal evaporation. So we usually put the pendant inside this hole, and after that we apply the current and heat it. So next I will talk about the E-beam evaporation. So we have thermal evaporation. Why we need the E-beam evaporation? So E-beam evaporation will give you much higher deposition rate because we use the electron beam to aim the source and to heat it until it vaporizes or sublimates. So the key part for the E-beam system is electron beam gun. So this is the filament which to emit the electrons. I just took a photo in case, because you don't have chance to see the filament in the system. So, and this the beam is coming from here. This is the assembling of E-beam. So usually the beam is bent at 270 degrees and to heat your material in this pocket. So we have the cooling underneath the heat and to cool down, because the temperature inside here is very high. If you melt like a temperature like a gold, it can reach 1,000 degrees here. And this is the E-beam evaporation system which in our facility. So we have so many different kind of materials for evaporation. We have lots of metal material and metal oxide material. So this is the schematic diagram of the E-beam system. So we have the E-beam source here. Once you heat to the source and then got evaporated, we have the shutter to control the deposition rate. So once the thickness is reached, and then the shutter will close automatically, and we have the quartz crystal to monitor the thickness. And during the deposition, the dome where the wafer sits also rotates to keep the uniformity higher. And so now I just compare the thermal evaporation and the E-beam evaporation. So I know in UQ we have like at least 2 thermal evaporation systems and probably another 2 or 3 E-beam evaporation systems. So why people use thermal evaporation? Thermal evaporation is very old technology, usually probably at the beginning, probably 50 years ago. And the deposition rate is very low, and usually it's for low melting point material. If it's a high melting point material, it's very hard to melt it. And another concern for thermal evaporation is the contamination, because you are heating the boat which contains the material. So you are heating the container, which is the boat and the source together, so may cause contamination from the boat. But the one good thing is for thermal evaporation is because the rate is low, it's good for organic material deposition. For E-beam deposition, so we'll have a large deposition rate and suitable for high melting point material. During the deposition, you can sweep the beam, which is to control, you can heat the source very uniformly. And for E-beam, we only heat the source, not the crucible, so we can minimize the contamination. Okay, let's talk about another PECVD technique. It's called sputtering. This is totally different from evaporation process. Sputtering is the process which the item are ejected or sputtered from the target and then deposited on your substrate as a result of ion bombardment to the target. So in this sputtering system, they involve ion bombardment. How to create this ion bombardment? So we need to have plasma. So in sputtering system, there's 2 types of sputtering. One is called DC sputtering, one is for RF sputtering. So DC sputtering usually is for conducting material like metals. RF sputtering can be used for anything, the metals, semiconductor, or insulators. The advantage for sputtering deposition, so any material you can be sputtered as long as you can find the target material. And in sputtering, we can do reactive sputtering, reactive deposition. That means during the deposition, you can induce the oxygen or nitrogen into the process, which you can form your oxide, metal oxide or nitride oxide and reactive material, like some compound material. And another advantage is the source and the substrate. You can place very close, which can improve the sputtering rate. And this is very important for industry. Usually they want everything is higher, the deposition rate as fast as possible. So basic mechanism of sputtering is just you, in the plasma system, in the plasma environment, you have the argon ions. This is the most commonly used ions. So you hit the target, which because here is a negative bias, because this is a cathode. So the argon will be accelerated to the target and hit the target, and then the sputtering item will be bounced to your substrate, and then you form the layer. So let's look at this DC sputtering. So we have two types of sputtering. One is DC, one is RF sputtering. So what is the DC sputtering? So DC sputtering is use DC electric current, which is very high voltage, is -2 to 5 kV, applied to the target. And the substrate, you can be grounded or biased. So the positive bias will accelerate the argon and strike the electrode where the target is. So the DC sputtering, the use of DC sputtering requires electrical conductivity. If it's not conductive, it's like if you use for insulating, the insulator, where the target is, will charge up and terminate the discharging, then you won't get any sputtering. So RF sputtering uses RF power with 13.56 megahertz frequency to glow discharge, which is good for insulating material. And in sputtering, the oscillating electrons are more efficient to ionize the gases, so which allow the RF sputtering to carry out at a very low pressure. So another topic is the sputtering yield or sputtering rate. When you do the sputtering, you care about this sputtering yield and sputtering rate. Everybody wants to have very fast sputtering rate. So sputtering yield is a little bit different. The concept is different from the sputtering rate. So sputtering rate, sputtering yield is, each material has their own characteristic sputtering yield. So sputtering yield, it depends on the incident energy, ions energy, and the masses of ions and the target material, and also the binding energy of the atom in the target, and the incidence angle of the ions. So sputtering rate is sputtering yield multiplied by the ion current. So there's a simple formula shows the sputtering rate, which is proportional to the power of the RF or DC power, and inversely proportional to the through distance and the pressure. Through distance usually refer to the target to the substrate distance. So if you have a higher power, definitely you'll get the higher deposition rate. If you reduce the pressure, and you will increase the sputtering rate as well. But there's some limitation of increasing the sputtering rate. You can have a higher power, but higher power may crack your target. And if you reduce the distance from target to substrate, it may affect your uniformity. So this is the summary of power density with different the target material. So when we apply the power to the target, usually we don't care about the maximum power. We more care about the power density for each side, each target. So right now we are using 4-inch size of target, like 10 centimeter of target in diameter. So if here is the recommended power density for different material. Like we use this no melting point metal like indium. So the maximum power in density is only 2 watts per centimeter square. So if you look at these 2 times the areas, the maximum power for this target is only about 160 watts. So you cannot use the power greater than 160 watts. If you apply it, you may crack or you may damage your target. So there's another technique called magnetron sputtering. So sputtering has been invented in 1940 or 50, but it didn't get used widely. It wasn't being used widely until the magnetron sputtering was invented. Because in the past, if you don't use magnetron sputtering, the deposition rate is very low. So how to increase the sputtering? So people think about use the magnet, just put behind the target, which to increase the percentage of electron, which to participate in ionization. So once you have more ionization, your sputtering efficiency will be increased and you will get higher deposition rate. So this is the sputtering target sputtering target, the source we have in our sputtering system. So this is the magnet in our chamber. So this is different polarity. This is the N north, one is the south. So this is a very strong magnet. Every time when I change the target, you can feel this strong magnet here. So another technique is called reactive sputtering. Reactive sputtering means we use another reactive gas to react with your target atom to form other compound material like oxide or nitride material. And another technique is called co-sputtering. Co-sputtering means you can use 2 or 3 sputtering at the same time, and then you get composition of different material. So like you can spot silicon and titanium at the same time, you can get titanium silicon material on your substrate. So here is the summary of the sputtering material we have in our facility. So we have a few oxide material and metal material as well. So usually for dielectric targets, you need to, when you order the target, you have to ask the supplier to make sure you have this backing plate on the back to protect your target. And for metal target, we usually don't need the backing plate. So let's compare the PVD process. So for e-beam evaporation, we usually get very high deposition rate at 1 to 2 angstrom per second, which is controllable. And the sputtering rate is usually very low. Only you can get 0.1 angstrom per second, sometimes even lower than this one. And for directional deposition, e-beam is very good, especially for leaf flow process. And the sputtering usually gives you a conformal deposition. So another issue is the adhesion. So e-beam generally give you a good adhesion, but for some noble metals like gold, platinum, or other material, you need like titanium or chrome as adhesion promoter. And the sputtering usually give you very good adhesion. And the cost, apart from the machine cost, the material cost, this is consumable cost. Usually for e-beam, you can just have very little of pellet, and then you can use it. For the target, you need to buy the whole target material, which is much expensive. Like for gold deposition, you can have, if for e-beam, you can just spend $100 to buy a small pellet. But for the target, it costs more than 10,000 for the target, but usually we don't use gold sputtering. So another features is for compound material deposition. So E-beam is very hard for compound material deposition because they have all the material has different melting point and a different vapor pressure. But for sputtering, yeah, we can do cold sputtering, we can do reactive sputtering, and we still can maintain stoichiometry. And the surface treatment. So you in sputtering system, usually you can use sputtering to clean the surface before you start deposition. So that means you can keep the surface very clean and fresh. So the next we will move to CVD process. So CVD process is totally different from PVD process. So chemical vapor deposition process, we use chemical reaction. So it's a method of forming a thin film on substrate by reaction of vapor-phase chemical, which contains required constituents. So we can decompose it of source gases by various energy forces such as heater, plasma, chemical, and other means. So the main steps in CVD is first you introduce the reactive gas into the chamber. Then after that, you use different means to activate the gas. And then the reactive species will absorb from your substrate surface, and then they go through chemical reaction and form a solid film. And the byproducts will be taken away to the exhaust. So what we have the PVD process. Why we need a CVD process? So CVD process can deposit single crystalline, polycrystalline, amorphous material, including single crystalline, silicon, amorphous silicon, all these silicon-based dielectrics. And also you can deposit high K electron dielectrics and the metals, especially in industry, people use tungsten CVD and copper CVD. The advantage of CVD, so it has very high growth rate and can deposit material which is hard to evaporate, and generally give you a very good quality of film. And the process usually is conformal. So disadvantage of a CVD process is the temperature. Usually the process will be carried out at a high temperature. It depends on what kind of CVD process you're using. And they also use lots of toxic or corrosive gases. First, I will talk about the LPCVD system. LPCVD, that means no pressure CVD method. So you use thermal energy, that means heater, to activate the gases. So usually the system, the process is carried out at 0.1 to 1 torr pressure at high temperature. And this CVD, LPCVD process is the batch process, so you can load 100 to 200 wafer per run. So the wafer can be stacked close, faced back to back together, and the temperature is controlled from 500 degrees to 900 degrees based on what kind of material you are using. And that's a typical LPCVD system. So for some good LPCVD system, you have a 5-zone temperature controller. So also have a pump here to maintain the low pressure. So the door will be closed, And this horizontal LPCVD system. In industry, usually people use a vertical system, which to improve the productivity. And I just listed some of LPCVD reactions. So there's 4 types of reaction. So the thermal, reduction, oxidation, and compound formation. So in semiconductors, usually these two processes very commonly used. So for polysilicon deposition, this we carry out at 650 degrees, use saline gas to decompose to the silicon, and amorphous silicon we're using same gas but use different temperature. And the TILS process, which to produce the oxide. And here, this is the nitride silicon, LP silicon nitride process, which usually we carry out at 700 to 800 degrees. We use dichlorine silane and ammonium to react to form this silicon nitride film. So the next is another CVD process. It's called plasma-enhanced CVD. So this CVD, we use plasma to transfer the energy and to activate the reactive gases. So this, compared with the LPCVD process, this is a low temperature process. Usually the temperature is less than 400 degrees. So when we use this process, because the advantage of the process is a low temperature process, so once you have the metal on your substrate on your device, it doesn't allow you to go to high temperature like LPCVD process. So you need to use the LPCVD PECVD process to deposit a layer like a passivation layer on your metal. The disadvantage of PECVD is because we're using plasma, they may cause plasma damage. The film is not very pure. There's a lot of hydrogen incorporated into the film, and the film density is not as good as LPCVD. And this is a typical PECVD process. This is all very common used in all research and industry. So for PECVD, we use silane and nitrate ammonium to react to get the silicon nitride. So this is a typical PECVD oxide process, and this is a amorphous silicon process, and this is a silicon carbon process. So PECVD amorphous silicon, this process has been studied very widely for solar cell researches. So let's compare different oxidation or silicon dioxide process. So we have PECVD oxide, LPCVD oxide, LPCVD TILS, all different kind of techniques. We all can get silicon dioxide. So what kind of property which they can is unique from others? So first, you look at the deposition temperature. So if you're looking at low temperature process, so you should look at the PECVD. So if you look at the step coverage, so probably you look at PECVD TILS. They give you much better conformal deposition. And also, there's another important feature, this etching rate. From the etching rate, you can see the PECVD silicon oxide has very high etching rate, which means the film is very loose. So that's compared with, you can see the thermal oxide has the best etching, the lowest etching rate. So that means the oxide film quality is the best. So here I compare the different CVD for nitride. So for LPCVD, PECVD, you can look at the temperature is totally different. And another two factors we need to look at is the percentage of hydrogen. So in LPCVD system, you will have very low hydrogen percentage. But PECVD, you will have much higher concentration. So another parameter you need to look at is the stress, whether you need a tensile or you need a compressive stress. So for PECVD, usually you can cue the process by changing the gas flow or other process parameters. So in general, there's the PECVD and the LPCVD system. So we just summarize here. I have mentioned previously. So LPCVD system usually give you very conformity, deposition, and a batch process, and you will have very high breakdown voltage. That means the film quality is very good. And PECVD usually carry out at low temperature. Disadvantages, so LPCVD using the high temperature and the low deposition rates. And the PECVD usually is a single wafer process, and the risk is for chemical contamination. And this is a typical temperature we're using for PECVD and LPCVD process. So next I will talk about atomic layer deposition. Atomic layer deposition is one atomic layer deposit in one cycle. So the process of this ALD is to there's a 4 steps sequence for this ALD process. So first you expose of the first precursor. So after that you purge in evacuation, then you get the first atomic layer deposit. After that, then you induce another second precursor into the chamber, and then you purge and evacuate. Then you get the second layer of atomic layers. So there are two types of ALD reactor. One is thermal ALD, another one is plasma as ALD. So plasma ALD usually give you a little bit higher deposition rate. So we have so many different deposition techniques. So what's the advantage for ALD? So ALD give you very precise thickness control, because every time you only glue one atomic layer, and you have a very good stoichiometric film, and it's a low temperature process, and it's a very gentle process. If you're using sensitive substrate, you can use ALD. But the disadvantage of ALD is the deposition rate is very low. So if you want to go for a very thick layer, you cannot choose ALD, because every time they only grow one atomic layer. So next, I will talk about the thermal oxidation process. This thermal oxidation is simple. You just use oxygen to oxidize the silicon surface to form of layer of silicon dioxide. So the temperature usually is more than 800 degrees. So there's two types of oxidation process. One is wet, one is dry process. Wet oxidation process usually use water, steam, or you use hydrogen and oxygen reaction to produce the water steam. This is give you a much better the quality. And wet oxidation usually has a faster growth rate, while the dry oxidation, the oxidation rate is very low. So when you do the oxidation, if you just do oxidation on your bare silicon wafer, probably you don't need to worry about how much the silicon will be consumed. But if you're making device, so you need to keep in mind, so oxidation process incurred 46% below the original surface, which as the silicon is consumed. So let's say you have 1 micron, you want to grow 1 micron oxide. So they will consume 0.46 micron silicon. So you will get totally 1 micron oxide, but below they will take away this oxide. So this is a typical horizontal oxidation furnace. The one thing is very important during the oxidation process is the cleaning. Before you put the wafer, load the wafer into the furnace, you must clean the wafer properly by RC or prana cleaning, which Annie mentioned. So this is very important because this will help you to remove all the particle, even some defects or something, which will affect the oxidation process. I know that in UQ probably there are a few oxidation furnaces around. So yeah, I don't know whether when you run the process, whether you follow this step. So usually after oxidation, you need to anneal the oxide layer because there's some defect at a high temperature. You need to anneal it after you finish the oxidation process. So I will compare this some typical thin film deposition technology. So we have thermal evaporation, E-beam evaporation, sputtering, PECVD, LPCVD, so many techniques. So what kind of material should be used for different process? So thermal evaporation usually for metal with no melting point material. So E-beam evaporation fits for both metal and some of dielectrics material. Sputtering can do anything. So PECVD usually for dielectrics, and LPCVD usually for silicon-based dielectrics. So when we choose the different technology, so we look at the impurity. One is very important for some research. So you look at this PECVD, usually the impurity is very low, and also the deposition rate. So sputtering usually gives you a very low sputter rate, especially for dielectrics material. And you look at the substrate temperature, usually thermal and E-beam evaporation, we carry out at room temperature, but during the process, the temperature will heat up to less than 100 degrees. And also is directional deposition. Yeah, so there's thermal and E-beam is directional, and PECVD is some degree. LP is conformal. So we are going to deposit. We have so many deposition technique. Once we have so many films, how to characterize this film? So there's a few different properties we need to look at. So there's surface structure. We can use a microscope or SEM or TMAF to look at the surface. And some physical structure, we can use stylus or optical profiler and X-ray and emissimeter to look at it, especially some optical property. And the chemical property is you need to look at different composition in the film.